Good morning. I am a student of BSc Chemistry Honours second year. Today we will discuss the chapter Electrochemistry. So let's start the chapter. What is an electrochemical cell or galvanic cell? Whenever a redox reaction is allowed to take place in a single beaker, it is found that the solution becomes hot. For example, when a zinc rod is placed in copper sulfate solution, the solution is found to be warmer as the reaction proceeds according to the equation. Zinc plus CuSO4 goes to zinc SO4 plus Cu. Similar results are observed when a rod of copper is placed in silver nitrate solution. The reaction taking place is as follows. It is also known as the displacement reaction. Thus, we conclude that whenever a redox reaction takes place in a single beaker, chemical energy in the form of heat is produced. By suitable means, it is possible to convert the chemical energy into electrical energy. A device used to convert the chemical energy produced in a redox reaction into electrical energy is called an electrochemical cell or simply a chemical cell. These are also called galvanic cells or voltaic cells, after the names of Luigi Galvani or Alessandro Volta, who were the first to perform experiments on the conversion of chemical energy into electrical energy. How a redox reaction can be used to produce electrical energy leading to the formation of an electrochemical cell can be understood by taking the above two examples of redox reactions again. Redox reaction between zinc and copper sulfate. The reaction is zinc plus copper sulfate goes to zinc sulfate plus copper. It may be written as zinc plus copper 2 positive goes to zinc 2 positive plus copper. This reaction may be split into two halves reactions as under. Zinc goes to zinc 2 positive plus 2 electron, where copper 2 positive plus 2 electron goes to copper atom. The first reaction is called the oxidation half reaction and the second reaction is called reduction half reaction. The reaction obtained by adding the two half cell reactions is called the overall reaction. Thus, if a redox reaction is allowed to take place in such a way that oxidation half reaction takes place in one beaker and the reduction half reaction in the other beaker, the electrons given out by the former will be taken up by the latter and a current will flow. This is achieved as follows. A zinc rod is placed in zinc sulfate solution taken in a beaker. A copper rod is placed in copper sulfate solution taken in another beaker. The two rods are connected by a wire and the two solutions are connected by a salt bridge. A salt bridge is U-shaped tube containing concentrated solution of an electrolyte like potassium chloride, potassium nitrate and potassium sulfate etc. or solidified solution of such an electrolyte in agar-agar and gelatin. The function of the salt bridge is to allow the movement of ions from one solution to the other without mixing of the two solutions. Thus, whereas electrons flow in the outer circuit in the wire, the inner circuit is completed by the flow of ions from one solution to the other through the salt bridge. The complete setup may be shown as we can see the figure. From anode there is movement of cations to cathode, and from cathode there is we can see the movement of anions to anode. Some important features of the above cell reaction may be summed up as follows. The zinc electrode at which oxidation takes place is called the anode. The copper electrode at which the reduction takes place is called the cathode. Since electrons are produced at the zinc electrode, it is designated as the negative pole. The other electrode, that is copper electrode, acts as positive pole. The electron flow from the negative pole to the positive pole in the external circuit. However, conventionally, this current is said to flow in the opposite direction. The oxidation of zinc into zinc ions produces excess of zinc 2 positive ions in the left beaker. Similarly, the reduction of copper ions to copper atoms leaves the excess sulfate ions in the solution in the right beaker. To maintain electrical neutrality of the solutions in the two beakers, the cations and anions move through the salt bridge. This helps to complete the inner circuit as already mentioned. As copper from copper sulfate solution is deposited on the copper electrode and sulfate ions migrate to the other side, the concentration of copper sulfate solution decreases as the cell operates. Consequently, the current falls with the passage of time. Evidently, the weight of copper rod will increase while that of zinc rod will be decreased as the cell works. The cell based on the above reaction is commonly called Daniell cell. A popular form of this cell is shown in figure 6.3. Have a look on figure 6.3, that is the Daniell cell. Here salt bridge is replaced by a porous pot through which the sulfate ions migrate from copper sulfate solution to the zinc sulfate solution. Redox reaction between copper and silver nitrate solution. The reaction is copper plus silver nitrate goes to copper nitrate plus silver, or it may be written as copper plus 2Ag positive goes to Cu2 positive plus 2Ag, that is silver. The two half reactions will be copper goes to copper 2 positive plus 2 electron, whereas 2 silver ions plus 2 electron goes to silver atom. Hence the cell may be set up as shown in figure 6.4. Here oxidation takes place at the copper electrode, therefore it acts as anode or negative pole. Reduction takes place at the silver electrode, it acts as cathode or the positive pole. The flow of conventional current is from silver to copper. In a similar manner, based upon any reaction, an electrochemical cell can be constructed. Here is the cell diagram for the copper and silver nitrate reactions. Here copper is get oxidized to copper 2 positive and silver ions are get reduced to silver atom. So let's know what is an electrolytic cell. If the aqueous solution of an electrolyte or the molten electrolyte is taken in a vessel and two metal rods are immersed into it and then connected to a battery as shown in figure 6.5, the ions start migrating towards the electrodes. The cation, that is the positive ions, towards the cathode connected to the negative of the battery, and anions, that is negative ions, towards the anode connected to the positive of the battery. The anions on reaching the anode lose electrons, that is oxidation takes place on the anode. The cations on reaching the cathode gain electrons, that is reduction takes place. Thus at anode B negative goes to B plus electron, that is oxidation, and at cathode A positive plus electron goes to A atom, that is reduction takes place on the cathode. Thus, a redox reaction takes place on supplying electrical energy resulting into the decomposition of the substance. Such an arrangement in which electrical energy is supplied to bring about the redox reaction, which is otherwise non-spontaneous, that is to bring about the decomposition of the electrolyte, a phenomena called electrolysis, is called an electrolytic cell. Difference between the electrochemical cell, that is the galvanic cell, and electrolytic cell. The main points of difference between an electrochemical cell and electrolytic cell may be summed up as follows. Electrochemical cell. It is a device to convert chemical energy into electrical energy. That is, electrical energy is produced as a result of redox reaction takes place. Whereas electrolytic cell is a device to convert electrical energy into chemical energy. That is, electrical energy is supplied to the electrolytic solution to bring about the redox reaction, that is electrolysis. Electrochemical cell is based upon redox reaction which is spontaneous. Electrolytic cell, the redox reaction is non-spontaneous and takes place only when electrical energy is supplied. In electrochemical cell, the two electrodes may be set up in solutions of the same or different electrolytes. The former are called concentration cells. In electrolytic cells, the two electrodes are set up in the same electrolytic solution. In electrochemical cell, electrode on which oxidation takes place is called the anode or the negative pole, and the electrode on which reduction takes place is called the cathode or positive pole. In electrolytic cell, the electrode which is connected to the negative terminal of the battery is called the cathode. The cations migrate to it which gain electrons and hence reduction takes place here. The other electrode is called the anode. In electrochemical cell, to set up this cell a salt bridge or a porous port is used, whereas in electrolytic cell no salt bridge is used in this case. So let's discuss about the representation of an electrochemical cell. An electrochemical cell is represented in a manner as illustrated below for the Daniell cell. We can see here the representation of electrochemical cell, that is, by convention, the electrode on which oxidation takes place is written on the left hand side and the other electrode on which reduction takes place is written on the right hand side. The electrode on the left hand side is written by writing the symbol of metal or the gas first, followed by the symbol of the ion with its concentration in brackets. The electrode on the right hand side is written by first writing the ion along with its concentration in brackets, followed by the symbol of the metal. Single vertical lines represent the phase boundaries of the electrodes, and the double line represent the salt bridge. C1 and C2 represent the concentration of zinc 2 positive ions and copper 2 positive ions respectively. In a similar manner, CuAg cell may be represented as, we can see the representation here for copper silver cell. Electrode potential. In a cell, oxidation takes place at one electrode and reduction at the other. In other words, one electrode has the tendency to lose electrons while the other has the tendency to gain electrons. The tendency of an electrode to lose or gain electrons when it is in contact with its own ions in its solution is called its electrode potential. The electrode potential is further termed as oxidation potential. If oxidation takes place at the electrode with respect to normal hydrogen electrode and is called the reduction potential. If reduction takes place at the electrode with respect to the normal hydrogen electrode, further, if in the half cell the metal rod is suspended in a solution of unit activity or 1 molar concentration, assuming the solution to be ideal, the temperature is kept at 25 degrees centigrade or 298 Kelvin. The electrode potential is called standard electrode potential, represented usually by E node. If a gas is involved, the standard conditions chosen are 1 atmospheric pressure and 25 degrees centigrade temperature, that is 298 Kelvin temperature. Then EMF of cell and its measurement. The force which causes the flow of electron from one electrode to the other and thus results in the flow of current is called electromotive force, usually represented by EMF and measured in volts. This force evidently arises because of the different electrode potential possessed by the two electrodes. Thus, electromotive force may also be defined as the difference of potentials which causes the current to flow from an electrode at higher potential to an electrode at a lower potential. If all the reactants and products are present in their standard state, that at 25 degrees centigrade, the EMF is called standard EMF. To measure the EMF of cell, the easiest way is to connect the two electrodes to a voltmeter. The potential difference, that is the voltage, can be read directly from the voltmeter. However, such a measurement suffers from the following two serious objections. First one is the voltmeter draws some current from the cell, thereby changing the EMF of the cell. Second point is, with appreciable flow of current, a part of the EMF will be utilized to overcome the internal resistance of the cell. To overcome the above objections, potentiometric method, which is based upon Pejendorf's compensation principle, is used for the accurate measurement of EMF. In this method, the unknown EMF is opposed by another known EMF until the two are equal. The general principle involved may be explained with the help of figure 6.6. AB is a stretched wire of uniform thickness. S is a standard cell whose EMF is known. It is connected to the ends A and B. X is a cell whose EMF is to be determined. One end of the cell X is connected to the end A and B, the other to the sliding contact jockey J through the galvanometer G in such a manner that it sends EMF in a direction opposite to that of the cell S. The sliding contact is moved along the wire AB till at a particular point, say C. No deflection is observed in the galvanometer. If E represents the EMF of standard cell S and Ex that of experimental cell X, then obviously Es is directly proportional to length AB, Ex is directly proportional to length AC, then the ratio of Ex to Es is length AC upon length AB. Thus, knowing Es and Ex can be calculated alternatively. Knowing the values of Es, the wire AC may be calibrated in volts to give the reading Ex directly. The above method gives accurate results only if the following conditions are satisfied. First condition is Es should be greater than Ex. Second point is the wire AB should be uniform. Third condition is the galvanometer should be highly sensitive. Alternatively, the following arrangement may be used. A cell S or a storage battery of voltage greater than that of standard cell S or that of the experiment cell X is connected to the ends A and B of the stretched uniform wire AB through the variable resistance R. The sliding contact is fixed at the point C. Key is inserted at A so that standard cell S in the circuit. The variable resistance R is adjusted till there is no deflection in the galvanometer G. If ES is the EMF of standard cell, then obviously ES is directly proportional to length AC dash. Now the key is removed from position A and inserted in position B so that the experimental cell X is in the circuit. The sliding contact J is moved along the wire AB till no deflection is observed in the galvanometer. Let us suppose that is occurs at the point C. Then if Ex is the unknown EMF, we have Ex directly proportional to length AC dash. Ex by Es goes to length AC upon length AC dash. Thus, knowing Ex can be calculated. Then we will discuss about standard cell. A standard cell is a cell which fulfills the following requirements. It has a constant value of EMF which is reproducible. The EMF does not change with the passage of time. The temperature coefficient of the EMF is very low. The best known cell which meets the above requirements approximately is the Western standard cell, the usual form of which is shown in figure 6.8. It consists of an H-shaped glass vessel. One of the limbs contains mercury covered with a paste of mercurous sulfate and mercury. This limb acts as anode. The other limb which acts as the cathode contains cadmium amalgam containing 12 to 14% of cadmium by weight. Amalgam covered with crystals of solid cadmium sulfate dot 8 by 3 H2O and then saturated cadmium sulfate solution. Short platinum wires are sealed into the bottoms of the limbs to make contact with the inactive materials. The limbs are finally closed with corks and sealing wax. The purpose of placing solid crystals of cadmium sulfate dot 8 by 3 H2O is to keep the cadmium sulfate solution saturated at all temperatures. The reaction taking place in the cell as follows. Cadmium plus mercuric sulfate goes to cadmium sulfate dot 8 by 3 H2O plus 2 Ag. The cell is reversible in the sense discussed in the next section. Reversible and irreversible cells. In thermodynamics, a reversible process is defined as a process in which the driving force infinitesimally small from the opposing force and the force can be applying force infinitesimally greater than the force already acting. The concept of reversible process is highly significant in thermodynamics because a number of relationships have been derived for the processes that are thermodynamically reversible. In a cell, chemical energy is converted into electrical energy. In order that the thermodynamic relations may be applicable to cells, the cell must operate under reversible conditions. A cell is said to be reversible if it satisfies the following three conditions. First condition is if an opposing EMF equal to that of cell is applied to the cell, no current should flow in the circuit and hence no chemical reaction takes place. Second condition is if an opposing EMF slightly smaller than that of cell is applied and infinitesimally small current should flow from the cell and small reaction should take place. Third condition is if an opposing EMF infinitesimally greater than that of cell is applied, then an infinite small current should flow in the opposite direction and infinite small reaction in the reverse direction should occur. If the above conditions are not satisfied, the cell is not to be irreversible. The cell is said to be irreversible. A well-known example of reversible cell is that of Daniell cell, consisting of a zinc electrode dipped in zinc sulfate solution and a copper electrode dipped in copper sulfate solution. When it is producing current, the reaction taking place in the cell. When an opposing EMF equal to that of the cell is applied, the reaction stops completely and no current flows at all. When an opposing EMF infinite smaller than that of cell is applied, an infinite small current flows from the cell and the above reaction is found to take place. If opposing EMF infinitesimally greater than that of cell is applied, an infinitesimal current flows in the opposite direction and the above reaction is found to take place in the reverse direction. In the potentiometric methods for the determination of EMF, as no current flows at the time of measurement, the conditions of reversibility is satisfied. Now let us consider the example of a cell which is irreversible. Consider a cell consisting of a zinc rod and a silver rod dipped in dilute sulfuric acid. When the two rods are connected with a wire, the following reaction takes place. Zinc plus H2SO4 goes to zinc sulfate plus H2. That is, zinc is oxidized to zinc 2 positive ions and H positive ions are reduced to H2 gas. In other words, zinc dissolved at one electrode and H2 gas is evolved at the other. Now, if the cell is connected to an external source of EMF, whose EMF is slightly greater than that of cell and opposing the cell, silver dissolves at one electrode and H2 gas is evolved at the other. That is, now oxidation takes place at the silver electrode and reduction at the other. Thus, though the above reaction cell can be made to satisfy the first condition of reversibility, that is, the direction of the current can be reversed by taking the opposing force infinitesimally greater than the driving force. The second condition of reversibility is not satisfied, that is, the chemical change is not reversed. Instead, a new chemical reaction takes place, hence, the above cell is not reversible and is irreversible. Such cells, however, do not have any thermodynamic significance. Then we will discuss about the reversible electrodes. Two electrodes of a reversible cell are called reversible electrodes. Each electrode is termed as reversible electrode because the half cell reaction occurring at the electrode can take place in the direct direction as well as in the reverse direction. The various reversible electrodes are classified into the following 5 different types. First, metal ion electrodes. Such an electrode consists of a metal dipped in the solution of its ions, that is, zinc rod dipped in zinc sulfate solution, copper rod dipped in copper sulfate solution, etc. Taking the example of copper ion electrode, when oxidation takes place at the electrode, the reaction may be represented as copper goes to copper 2 positive plus 2 electrons. On the other hand, when reduction takes place at the electrode, the reaction may be represented as copper 2 positive plus 2 electron goes to copper atom. Thus, the electrode is reversible with respect to copper ions. Second electrode is amalgam electrodes. These electrodes are just like metal ion electrodes except that the metal is replaced by its amalgam, that is solution of the metal in mercury. For example, zinc amalgam electrode consists of zinc amalgam dipped into a solution of zinc ions. The electrode is thus represented as zinc mercury slash zinc 2 positive. When oxidation takes place at the electrode, the electrode reaction goes to zinc mercury to zinc 2 positive plus 2 electrons. When reduction takes at the electrode, the reverse reaction is written as zinc 2 positive plus 2 electron goes to zinc amalgam. Thus, the electrode is reversible with respect to zinc ions. Amalgam electrodes are preferred over metal ion electrodes for the following reasons. First reason is equilibrium between the amalgam and the ions is established more quickly than with the pure metal. Second condition is active metals like sodium, potassium, calcium, etc. cannot be used directly as electrodes in aqueous solutions. However, by changing them into amalgams, their activity is reduced and then they can be used. Third reason is the impurities present in metals, which sometimes cause erratic behavior in pure metals, are diluted by amalgamation to give satisfactory results. Third type of the electrode is gas electrodes. These electrodes consist of a gas bubble around an inert metal wire or foil, usually of platinized platinum, immersed in the solution capable of furnishing the ions of the gas. The function of the metal wire or the foil is that firstly, it helps to establish the equilibrium between the gas and its ions, and secondly, it helps to make an electrical contact, that is, electrons lost or gained can flow through it. A few common gas electrodes are briefly discussed below. First type of gas electrode is hydrogen electrode. The design of hydrogen electrode, which is in fact a general design for any gas electrode, is shown in the figure 6.10. In the standard or normal hydrogen electrode, hydrogen gas at 1 atmospheric pressure is passed into 1 molar HCl acid in which the foil of platinized platinum remains immersed. When in a cell, this electrode acts as the anode, that is, oxidation takes place. The following reaction takes place: H2 goes to 2H positive ions plus 2 electrons. That is, some hydrogen gas changes into H positive ions which go into the solution. When this electrode acts as cathode, that is, reduction takes place, the following reaction occurs: 2H positive plus 2 electron goes to hydrogen gas. That is, some H positive ions from the solution changes into H2 gas. Thus, the electrode is reversible with respect to H positive ions. This electrode is usually represented as platinum H2 gas slash H positive. Concentration is here represented by C. Second type of gas electrode is chlorine electrode. In this case, chlorine gas at a given pressure is passed into HCl acid, which is capable of furnishing the Cl negative ions. For oxidation to take place, the following reaction occurs: 2 Cl negative goes to Cl2 gas plus 2 electrons. For the reduction to occur, the following reaction takes place: chlorine gas plus 2 electron goes to 2 Cl negative ions. Thus, the electrode is reversible with respect to Cl negative ions. Third type of gas electrode is oxygen electrode. This electrode is reversible with respect to hydroxyl ions. Thus, to construct this electrode, oxygen gas at given pressure is passed into solution capable of giving OH negative ions. For reduction to occur, the reaction taking place is O2 plus 2H2O plus 2 electrons goes to 4 OH negative ions. For oxidation to occur, the reverse reaction takes place. Fourth type of electrodes is metal insoluble salt anion electrodes. This is most commonly employed category of electrodes. Here the electrode consists of a metal in contact with its sparingly soluble salt and solution of soluble salt containing the same anion as that of sparingly soluble salt. A few examples of the electrodes of this type are: first, AgCl KCl electrode, prepared by dipping a silver wire in KCl solution to which a drop of AgNO3 is added. Second, lead sulfate potassium sulfate electrode, prepared by dipping a lead wire in K2SO4 solution to which a few drops of lead nitrate solution are added to form lead sulfate. Third, Hg2Cl2 KCl electrode, that is calomel electrode. This is the most frequently used electrode. Is shown in figure 6.11. It is prepared as follows. Pure mercury is placed at the bottom of a tube T. It is covered with a paste of mercurous chloride calomel and then filled with either decinormal or normal or saturated solution of KCl from the side tube A, such that the side tube B ending into a jet is also filled with the KCl solution. A tube C having a piece of platinum wire sealed at its ends is fixed into the tube T, such that the platinum wire remains dipped into the mercury. A little mercury is placed in the tube C and a copper wire put into it to make an electrical contact. An alternative form of calomel electrode used as frequently in the laboratory and is shown in figure 6.12. Oxidation can occur at this electrode through the following reactions. Mercury goes to mercury 2 positive plus 2 electron, and then it adds to chlorine negative ions to form mercury chloride. Reduction can occur at this electrode through the following reaction. Mercury chloride goes to mercury 2 positive plus 2 Cl negative ions. This overall reaction is just the reverse of the overall reaction when oxidation takes place. Hence, the calomel is reversible with respect to chloride ions. Fifth type of electrode is oxidation reduction electrodes. These electrodes are prepared by dipping a platinum wire into the solution of two salts of the same metal but having different valencies. For example, ferrous and ferric salts, stannous and stannic salts, or cerous and ceric salts. The EMF arises because of the tendency of the metal ion in one oxidation state to pass into the second, more stable state. The function of the platinum wire is merely to pick up the electrons and to make an electrical contact to the electrode. The reactions taking place in such an electrode may be represented as follows. Fe2 positive goes to Fe3 positive plus electron. Sn2 positive goes to Sn4 positive plus 2 electron. Cerium 2 positive goes to Cerium 3 positive plus 1 electron. Then after this we will discuss about the relationship between electrical energy and chemical energy. The electrical energy produced in a cell is defined as the product of the quantity of electricity that passes through the cell and the EMF of the cell, that is electrical energy, is equal to quantity of electricity into EMF. For every 1 mole of electrons transferred in the cell reaction, that is for every 1 gram equivalent of the ions deposited, the quantity of electricity that flows through the cell is 1 Faraday. 1 farad is equal to 96,500 coulombs. Thus, if n moles of electrons are transferred in any cell reaction, for example, for the reaction zinc plus copper 2 positive goes to copper, n is equal to 2. The quantity of electricity passing through the cell is equal to n Faradays. If E is the EMF of the cell, then electrical energy is equal to NFE. Till the middle of the 19th century, it was generally accepted that the electrical energy produced in a reversible cell was equal to the chemical energy, measured as heat when the reaction takes place in a single beaker. This view was supported by the following results. In Daniell cell, N is equal to 2. Hence, in order that 2 gram equivalents of copper may be deposited or 2 gram equivalents of zinc may dissolve, 2 Faradays of electricity must flow through the cell. Further, for this cell, E is equal to 1.10 volt. Hence, electrical energy produced is 2 into 96,500 Faradays into 1.10 joules, that is equal to 2,12,300 joules. The heat produced when 2 gram equivalent of zinc react with the same copper sulfate solution in a single beaker is found to be nearly 2,12,000 joules. This is in good agreement with the electrical energy. However, later on it was observed that for a large number of reactions the electrical energy produced was not equal to the chemical energy. Hence, it was suggested by Gibbs in 1875 and Helmholtz in 1882 that the electrical energy produced in a reversible cell is equal to the decrease in free energy accompanying the cell reaction. Thus, if delta G represents the change in free energy, we must have minus delta G is equal to NFE. Further, according to the Gibbs-Helmholtz equation, we have delta G is equal to delta H plus T curl of delta G by curly T at constant pressure. Substituting the value of delta G from equation 1, we get minus of NFE is equal to delta H plus T in the bracket curl minus NFE upon curly T at constant pressure. Here we get E is equal to minus delta H by NF plus T into curly E by curly T and constant pressure. From equation 3, it is evident that whether electrical energy NFE produced is equal to, less than or greater than the enthalpy change delta H depends upon the sign of curly E by curly T, that is the temperature coefficient of EMF. Thus, if curly E by curly T is extremely small, almost equal to 0, as is the case in Daniell cell, the electrical energy produced is equal to the enthalpy change. Second case, if curly E by curly T is positive, the electrical energy produced is greater than the heat of reaction at constant pressure, the additional energy being absorbed from the surroundings. Third condition is if curly E by curly T is negative, the electrical energy produced is less than the heat of reaction at constant pressure, the difference of energy being lost as heat to the surroundings. Then we will discuss about the calculation of thermodynamic quantities of cell reactions, that is delta G, delta H and delta S. As already explained above, delta G is related to EMF according to the expression delta G is equals to minus NFE. Thus knowing the EMF E, delta G can be calculated. Thus, knowing the EMF E and the temperature coefficient of the EMF, the heat of reaction delta H can be calculated. Having known the values of delta G and delta H, the entropy change, that is delta S, accompanying the reaction can be calculated using the relationship delta G is equals to delta H minus T delta S, or a direct relationship for delta S in terms of EMF can be obtained as follows. From equation 2, delta G minus delta H is equals to T into curly of delta G by curly T at constant pressure, that is equal to minus NFT curly E by curly T at constant pressure. Comparing the equations, we get del S is equals to NF into curly E by curly T at constant pressure. Thus, the entropy change delta S can be calculated directly from the knowledge of the temperature coefficient of the EMF. Standard hydrogen electrode and measurement of electrode potential. The term electrode potential and standard electrode potential have already been defined in section 6.9. The absolute value of potential of a single electrode cannot be determined if can only be measured by using some electrode as the reference electrode. The reference electrode used as is the standard hydrogen electrode, in which H2 gas is at 1 atmospheric pressure is bubbled around a platinum foil dipped into the acid solution having H positive is equals to 1 molar. The electrode potential of the standard hydrogen electrode is taken as 0. To determine the electrode potential of any electrode, a cell is set up using the electrode as one of the electrodes and the second electrode is the standard hydrogen electrode. The EMF of the cell is measured. As the EMF of the cell is the sum of the oxidation potential of the electrode where oxidation takes place and the reduction potential of the electrode where reduction takes place, and one of the electrodes involved is the standard hydrogen electrode, for which the electrode potential is taken as 0. The EMF of the cell which will directly give the electrode potential of the electrode under investigation. The direction of the flow of current further indicates whether oxidation takes place or the reduction takes place on the electrode under investigation with respect to the hydrogen electrode. Accordingly, the electrode potential is termed as oxidation potential and or reduction potential. The determination of electrode potential may be further illustrated with the help of following two simple examples. First is determination of standard electrode potential of zinc to to positive electrode. A cell comprising of zinc electrode immersed in 1 molar zinc sulfate solution and a standard hydrogen electrode is set up as follows. EMF of the above cell comes out to be 0.76 volt. Hence, standard electrode potential of zinc 2 positive electrode is equals to 0.76 volt. Further, the direction of flow of current indicates that oxidation takes place at zinc electrode. Hence, 0.76 volt is standard oxidation potential of zinc 2 positive electrode. Second example is determination of standard electrode potential of copper 2 positive electrode. A cell comprising of copper electrode immersed in 1 molar copper sulfate solution and standard hydrogen electrode is set up as follows. Have a look on this diagram which shows the measurement of standard electrode potential of copper to 2 copper positive electrode using standard hydrogen electrode as the reference electrode. EMF of the cell comes out to be 0.34 volts. Here, hence, standard electrode potential of copper 2 positive electrode is 0.34 volt. Further, the direction of flow of current indicates that reduction takes place at the copper electrode. Hence, 0.34 volt is the standard reduction potential of copper to copper 2 positive electrodes. It is important to mention here that it is common practice to express all the electrode potential as reduction potentials, since the reduction half reaction is just the reverse of the oxidation half reaction. Therefore, reduction potential is obtained from the oxidation of potential by simple changing the sign. That is, for any electrode, reduction potential is equal to negative of oxidation potential. So let's discuss about other reference electrodes and measurement of electrode potential. The use of hydrogen electrode as the reference electrode is not convenient obviously because it involves the use of H2 gas. Hence a number of other electrodes have been used as reference electrodes. The most common out of these is the calomel electrode, the construction of which has already been described in figures 6.11 and 6.12. The electrode potential of the calomel electrode at 25 degrees Celsius using zero point 0.1 normal KCl and 1.0 normal KCl and saturated KCl solution have been determined accurately. These are given below as reduction potentials. Zero point 0.1 normal KCl has the reduction potential 0.3338 volt. 1.0 normal KCl solution has the reduction potential as 0.2800 volt. Saturated KCl solution has the reduction potential equals to 0.2415 volt. To determine the electrode potential of any electrode, a cell using this as one of the electrodes and calomel electrode as the second electrode is set up. The EMF of cell is measured and then the following expression is used to calculate the required electrode potential. EMF of the cell is equal to oxidation potential of the electrode where oxidation takes place plus reduction potential of electrode where reduction takes place. The calomel electrode using zero point 0.1 normal KCl solution is usually preferred because it has lowest temperature efficient. However, the calomel electrode using saturated KCl solution is convenient for many purposes and is still used. The method of determination of electrode potential using calomel electrode as the reference electrode is to be illustrated with the help of following examples. First example is determination of standard electrode potential of zinc 2 positive electrode. A cell comprising of zinc electrode immersed in 1 molar zinc sulfate solution and the calomel electrode is set up as follows. EMF of the above cell at 25 degrees centigrade comes out to be 1.083 volt. Further, the direction of flow of current shows that oxidation takes place at the zinc electrode. Hence, we have EMF of the cell is equals to oxidation potential plus reduction potential of the calomel electrode. That is 1.083 is equal to oxidation potential of zinc electrode. Second example is determination of the standard electrode potential of copper to copper 2 positive electrode. A cell comprising of copper electrode immersed in 1 molar copper sulfate solution and the calomel electrode say using 1 normal KCl solution is set up as shown in figure 6.16. EMF of the above cell comes out to be 0.018 volt. Further, the direction of flow or current shows that reduction takes place at the copper electrode. Hence, we have EMF of the cell is equals to oxidation potential of the calomel electrode plus reduction potential of the copper electrode. 0.018 is equals to minus 0.280 plus reduction potential of the copper electrode. So the reduction potential of the copper electrode will comes out to be 0.298 volt. Similarly, silver in the silver chloride electrode has also been used as reference electrode. Its standard electrode potential has been found to be plus 0.02224 volt at 25 degrees Celsius temperature. Then we will discuss about electrochemical series. The standard electrode potential of a large number of electrodes have been determined using standard hydrogen electrode as the reference electrode, for which the electrode potential has been arbitrarily fixed as zero. Also, as already mentioned, it is a practice to express the electrode potentials as reduction potentials. Since reduction half reaction is just the reverse of oxidation half reaction, the reduction potential of any electrode is obtained from its oxidation potential by simply changing the sign. Further, according to the latest conventions of sign, the electrode at which reduction takes place with respect to either standard hydrogen electrode has a positive oxidation potential or expressed as reduction potential, it will have a negative sign. The various electrodes have thus been arranged in order to their decreasing values of standard reduction potentials as shown in table 6.2. This arrangement is called electrochemical series. Then we will discuss about the applications of electrochemical series. First application is to predict the relative ease of oxidation or reduction of various elements. As by convention, positive sign is used to represent the reduction potential. This implies that greater is the reduction potential, more easily is the substance reduced, or in other words, stronger oxidizing agent. F2 has the highest reduction potential and lithium positive ion has the lowest reduction potential. This means that F2 is reduced most easily, whereas lithium positive ions are reduced with greatest difficulty. In other words, F2 is the strongest oxidizing agent, whereas lithium positive ions are the weakest oxidizing agent. Conversely, writing the reactions in the reverse order, it can be postulated that lithium will be oxidized most easily and hence is best reducing agent, whereas fluoride negative ions are oxidized with greatest difficulty and hence are weakest reducing agent. Here it's the electrochemical series in which we can see the reduction potentials and oxidation potentials of different ions. Second application of electrochemical series is to predict whether a metal reacts with acid to give hydrogen gas. In order that metal M may react with an acid to give H2 gas, the following reaction should take place. Metal plus H positive goes to metal positive plus half H2, which can split into two half reactions as metal goes to metal positive plus 1 electron, whereas H positive plus electron goes to half H2, that is the reduction half reaction. The metal should have the tendency to lose electrons, that is undergo oxidation with respect to hydrogen. In other words, the metal would have a negative reduction potential. Thus, all metals lying below hydrogen in the electrochemical series react with the acid to give hydrogen gas. Further, evidently lower the reduction potential, higher is the reactivity. Alternatively, as we will see later, the EMF of the cell comprising of the oxidation half reaction and reduction half reaction as written above may be calculated by adding the oxidation half potential and the reduction half potential. If EMF comes out to be positive, the reaction takes place. Third application of the electrochemical series is to calculate the standard EMF of any electrochemical cell, as electrochemical cell is based on the redox reaction, which can be split into two half reactions, that is oxidation half reaction and the other one is reduction half reaction. So the standard EMF of the cell will be equal to standard oxidation potential of the oxidation half reaction plus standard reduction potential of the reduction half reaction. Also, as oxidation potential is equals to minus reduction potential, the above expression may also be written in the form of as standard EMF of the cell is equal to standard reduction potential of the reduction half reaction minus standard reduction potential of the oxidation half reaction. Further, as in the representation of cell, the electrode on which oxidation takes place is written on the left hand side, and the oxidation and the electrode on which reduction takes place is written on the right hand side. As already discussed, we have discussed it in the section 6.3. The above expression may also be written as standard EMF of the cell will be standard reduction potential of right hand side electrode minus standard reduction potential of the left hand side electrode, that is equal to E node of the cathode minus E node at anode. This method of calculation is illustrated with the solved numericals. Here are some numericals. After doing the numericals, we will discuss about the point, that is polarization. If a cell consists of two reversible electrodes, then as the cell operates at each electrode, the rate of discharge of ions and the rate of their formation are equal. That is, electrode is in the state of equilibrium. Hence, there is no net flow of current. However, if the rate of discharge of ions is not equal to their rate of formation, equilibrium at the electrode is disturbed and a current may flow through the cell. This disturbance of equilibrium associated with the flow of current is called electrode polarization, and the disturbed electrode is said to be polarized. Such an electrode is said to behave as an irreversible electrode. The simplest type of polarization is known as concentration polarization, as briefly explained below. Suppose a reversible electrode is set up by dipping a metal rod in the solution of its own ions. Then it will have a definite electrode potential depending upon the concentration of the ions, as calculated by applying Nernst's equation. If this electrode is made the cathode in an electrolytic cell and potential just greater than its reversible electrode potential is applied, thus then as reduction takes place at the cathode, the reaction Mn positive plus N electron goes to metal will start taking place. That is, discharge of metal ions will start on the metal electrode. As a result, the concentration of metal ions in the vicinity of this electrode will start decreasing. If the ions from the bulk of the solution do not diffuse towards the electrode to make up the loss, there is a fall in concentration of the ions around the electrode, and hence its electrode potential will decrease in accordance with Nernst's equation. Similarly, if the electrode is made the anode in the electrolytic cell and a potential just greater than its reversible electrode potential is applied, then as oxidation takes place on the anode, the reaction occurring at the anode is M goes to Mn positive plus N electron, that is, metal will dissolve to produce metal ions. As a result, concentration of metal ions around the electrode will increase. If the excess ions do not diffuse away from the electrode into the bulk of the solution, the concentration of metal ions around the electrode will begin to increase, and so its electrode potential will also begin to increase in accordance with the Nernst equation. The increase or decrease in the concentration of metal ions around an electrode during electrolysis, resulting into increase or decrease in the value of its electrode potential, then the reversible electrode potential value is called concentration polarization. Evidently, concentration polarization arises on account of the slow diffusion of ions from the electrode if the solution is stirred during electrolysis. Concentration polarization is almost reduced to zero. This is because stirring quick migration of the ions takes place. Here our chapter has come to the end. Thank you.